This is how we can represent an electrode reaction. And we can write the respective Nernst equation. We can write the Nernst equation for that electrode reaction. You have already written that equation. And from that equation, it is clear that potential of an electrode, potential of an electrode, each cell, depends on concentration of the ion to which it is reversible. Potential of an electrode. Here, the Mn plus bar M electrode. Its potential depends on the ion, that is Mn plus, to which it is reversible. Means that reaction is reversible with respect to Mn plus ion. That is from Nernst equation. Potential of an electrode in cell depends on concentration of the ion to which it is reversible. So based on this electrode potential, we can do this potentiometric titration. We know the relationship between electrode potential and concentration of the ion. So we can set up an experiment known as potentiometric titration based on the principle change in there will be a change in electrode potential with respect to the addition of titrant. Or using potentiometric titration, we can measure change in electrode potential with the addition of titrant. You know we are taking titrant in the burette and we have an analyte in beaker or a conical flask. And we are adding our titrant to the conical flask. We have a setup to measure electrode potential. So the system is a burette consists of titrant and there is a conical flask containing analyte and there is a cell setup to measure electrode potential of the system. As we add titrant to the conical flask, there will be a change in the concentration of Mn plus ion. There will be a change in the Mn plus ions. Accordingly, there will be a corresponding change in the electrode potential. We can measure it using voltmeter. This is the principle of potentiometric titration. And there are three types of potentiometric titrations. You know the second type, acid-base titration. And I think you are unfamiliar with oxidation reduction titration and precipitation titration. You know about acid-base titration. It is a type of potentiometric titration. And the other remaining two, they are oxidation reduction titrations and precipitation titrations. And yesterday we discussed the argenometric method. If you remember, during our lab session, we have discussed an experiment to determine the amount of chloride present in water. During our lab session, we have discussed that experiment. And there was a collection from yellow to red. And I told that there is red color due to the formation of a precipitate. So that reaction is known as precipitation titration. And here we have to discuss redox titrations in detail. ഇതിൽ നിങ്ങൾക്ക് വേറെ ഏതെങ്കിലും ടൈട്രേഷൻ അറിയാവുന്നതുണ്ടോ? ആസിഡ് ബേസ് ടൈട്രേഷൻ അല്ലാതെ വേറെ ഏതെങ്കിലും ടൈട്രേഷൻ അറിയുന്നതായിട്ടുണ്ടോ? Yes or no? You know acid-base titration. Okay. Okay, then we can discuss about acid-base titration. So if we are doing an acid-base titration, we are taking either acid as our titrant or base as our titrant. Normally, acid ആണ് titrant ആയിട്ട് എടുക്കുന്നത് അല്ലേ? പുറത്തിൽ എടുക്കുന്നത് acid ആണ്. And how can we do that titration? We are adding titrant to the analyte. We are adding titrant to the analyte. Then how can we determine the endpoint? How do we determine the endpoint of an acid-base titration? Yes, there will be a color change. ആ കളർ ചേഞ്ചിന് റീസൺ എന്താണ്? ആസിഡും ബേസും നമ്മൾ എടുത്തുള്ളൂ. pH value. Okay. We are adding a reagent, right? We are adding a reagent. It is known as an indicator. We are adding an indicator. And as we said, there will be a change in pH value. And as there will be a color change according. Due to the pH change, there will be a color change. And which is the reaction during acid-base titration? Is it oxidation, reduction, or anything else? What is the reaction during acid-base titration? Is it oxidation, reduction, precipitation, or anything else? Hope you know about neutralization. It is neutralization. Yes, Vida. It is neutralization reaction. We are taking acid and base, and there will be a pH corresponding to the neutralization reaction. At that pH, the color of the solution changes. And we are noting the volume of titrant taken in the burette. We are noting that volume. And in redox titration, that is oxidation, reduction, titration, we are not using an indicator. We are not using an indicator solution. ഇവിടെ ഈ redox titration നമ്മൾ ഇൻഡിക്കേറ്റർ യൂസ് ചെയ്യുന്നില്ല. ഓക്കെ, നമ്മൾ അവിടെ യൂസ് ചെയ്യുന്നത് ഒരു ഇൻഡിക്കേറ്റർ ഇലക്ട്രോഡാണ്. ഇൻഡിക്കേറ്റർ ഇലക്ട്രോഡ്. ഈ ഇൻഡിക്കേറ്ററുമായിട്ട് ഒരു സൊല്യൂഷൻ നമ്മൾ ആഡ് ചെയ്യുന്നില്ല. യൂസ് ചെയ്യുന്നത് ഇൻഡിക്കേറ്റർ ഇലക്ട്രോഡാണ്. ഇൻഡിക്കേറ്റർ ഒന്നും യൂസ് ചെയ്യാത്തത് കൊണ്ട് തന്നെ അവിടെ കളർ ചേഞ്ച് നോക്കിയിട്ടല്ല എൻ പോയിന്റ് ഡിറ്റർമിൻ ചെയ്യുന്നത്. പിന്നെ എങ്ങനെയാണ് റിഡോക്സ് ടൈട്രേഷനെ യൂസ് ചെയ്ത് എൻ പോയിന്റ് ഡിറ്റർമിൻ ചെയ്യുന്നത്? As we said, the acid-base titration involves neutralization reaction. In redox titration, the reaction is redox reaction. There will be redox reaction between the analyte and the titrant. This is the reaction. using inert platinum electrode, which is our indicator electrode. Inert platinum electrode, it is used as the indicator electrode, and it is dipped in a solution containing ions which are oxidized and reduced to. Imagine you have a solution containing Fe2 plus and Fe3 plus ions. Means ions of the same species, Fe2 plus and Fe3 plus. Here Fe2 plus, it is the reduced form, Fe2 plus. And Fe3 plus is the oxidized form. So ions of the same species, ions of iron, Fe, and they are in both oxidized and reduced forms, Fe3 plus and Fe2 plus. So this step is clear, I think. We are dipping an inert indicator electrode. You can use platinum. It is dipped in a solution containing both oxidized and reduced forms of ions of same species. Now we have to measure electrode potential. We have indicator electrode, but we have to measure electrode potential. So we have to couple the platinum electrode with, with a reference electrode. We have to couple the platinum electrode with a reference electrode. So we use Calomel electrode as our reference electrode. ഇവിടെ coupled platinum electrode, when we dip this platinum electrode in the solution, the platinum electrode becomes a redox electrode. That is this redox electrode. When we dip the platinum electrode in this solution, it will become redox electrode. Then how will be the reaction? There will be an oxidized state, Fe3 plus a number of electrons gives a reduced state. You know, we are taking a solution containing ions in the oxidized and reduced forms. In this oxidized state, excess electrons get reduced. This is the general reduction reaction that will be happening during redox titration. And we can determine potential of the indicator electrode using this equation. Using our Nernst equation. E equal to E0 minus 0.0591 divided by N log concentration of oxidized state divided by reduced state. This is how we can determine the potential of the indicator electrode. And the endpoint determination. The endpoint determination can be done by potentiometric titration. I think you have some idea about redox titration. And we have to discuss the procedure of a redox titration. It will be more clear if we are discussing the procedure. ഇതിനെക്കുറിച്ച് ചെറിയൊരു ഐഡിയ ഒക്കെ കിട്ടിയില്ലേ? എങ്ങനെയാണ്, എന്താണ് റിയാക്ഷൻ, എങ്ങനെയാണ് സ്റ്റെപ്പ് ചെയ്യുന്നത് എന്നൊക്കെ ഒരു ഐഡിയ കിട്ടിയില്ലേ? Okay. Then how can we perform a redox titration? You can see here there is a figure to help you. We are taking 20 ml ferrous sulfate solution. ferrous sulfate, iron exists in Fe2 plus state. Ferrous. This Fe2 plus. So we have solution containing Fe2 plus ions in a beaker. It is a ferrous sulfate solution in a beaker, and we are adding sulfuric acid. We are adding sulfuric acid to the beaker. Why do we add sulfuric acid? We need for a sulfate solution, but we are adding sulfuric acid. Why do we add sulfuric acid? Any guess? We are adding sulfuric acid because we need an acidic medium. Since we need an acidic medium for the reaction, we are adding sulfuric acid. That is the reason. We have added sulfuric acid in the beaker, and a platinum electrode is dipped in the beaker. You can see here there is a platinum wire which is dipped in the beaker. And we have to measure electrode potential. So we are coupling the platinum electrode. We are coupling we are coupling a calomel electrode with the platinum electrode. Since we need to measure the electrode potential, we are coupling a calomel electrode with the platinum electrode, and there is a voltmeter to determine the electrode potential to read that value. So this is our setup of the redox titration. This is our analyte. Now we need our titrant. Here our titrant is ferric ammonium sulfate solution. This is the titrant which is taken in the burette. Ferric ammonium sulfate. In ferric ammonium sulfate, cerium Ce exists in the 4 plus oxidation state. Ce4 plus. So we have our titrant containing Ce4 plus ions and analyte containing Fe2 plus ions. Now we are starting our titration. We are adding Ce4 plus ions into the Fe2 plus ions. And we are adding 1 ml of Ce4 plus. Then we are noting the reading in the voltmeter. We are adding 1 ml of Ce4 plus and noting the voltmeter reading. Then again adding 1 ml Ce4 plus, we are noting the value on the voltmeter. Similarly, we are repeating the procedure, adding 1 ml and noting the voltmeter reading. Near the end point, we are adding drop wise. We are adding Ce4 plus in drop wise. Adding 1 drop, then note the value. Again add 1 drop of Ce4 plus. We have to note the value in the voltmeter. And finally, we get the values of voltmeter corresponding to the value of volume of Cm4 plus. We will have two values, one for volume of Ce4 plus and its corresponding voltmeter reading. And we are plotting a graph. volume of cerium 4 plus versus potential at the calomel electrode. We are plotting a graph and it will be like this. There will be a sigmoid curve. You can see here there is a slight increase in the potential as we are adding cerium 4 plus. There is only slight increase in the potential. But as we add cerium 4 plus continuously, there is a sharp increase in the potential. Here there is a sharp increase in the potential. This indicates here is the endpoint. The endpoint is near the sharp increase of the potential. ഈ ഒരു ഗ്രാഫ് നിങ്ങൾക്ക് നോക്കിയാൽ അറിയാം ഇവിടെ വരുന്നത് ആദ്യമൊക്കെ ചെറിയ ഇൻക്രീസ് മാത്രമാണ്. വോളിയം ഓഫ് സീറിയം 4 പ്ലസ് ആഡ് ചെയ്യുന്നതിനനുസരിച്ച് ചെറിയൊരു ഇൻക്രീസ് പൊട്ടൻഷ്യൽ മാത്രമേ ഉണ്ടാവുന്നുള്ളൂ. ഇവിടെ ഒരു പോയിന്റ് എത്തുമ്പോഴേക്കും വോളിയം ഓഫ് സെറിയം 4 പ്ലസ് അതൊരു ഡ്രോപ്പ് ആഡ് ചെയ്താൽ ഈ പൊട്ടൻഷ്യൽ ഷാർപ്പ് ഇൻക്രീസ് ആണ് ഉണ്ടാവുന്നത്. അതാണ് ഇൻഡിക്കേറ്റ് ചെയ്യുന്നത് ഈ ഒരു ടൈട്രേഷന്റെ എൻഡ് പോയിന്റ് വരുന്നത് ഈ ഒരു റീജിയനിലാണ്. ഈ ഒരു ഷാർപ്പ് ഇൻക്രീസ് വരുന്ന റീജിയനിലാണ് എൻഡ് പോയിന്റ് വരുന്നത് എന്ന്. Then how can we determine the end point? We have this straight line and half of this value, exact half of this value will give you the end point. Here we are not noting the color change. We are noting the end point based on this graph. മനസ്സിലായോ ഇവിടെ നടക്കുന്ന പ്രൊസീജിയർ എന്താണെന്നും എങ്ങനെയാണ് ഈ ഗ്രാഫ് പ്ലോട്ട് ചെയ്യുന്നതെന്നൊക്കെ മനസ്സിലായോ? റിപ്പീറ്റ് ചെയ്യണമെങ്കിൽ പറയാട്ടോ. ഓക്കെ, എനിക്ക് തോന്നി വേണ്ടി വരുന്നു. I think it is clear. We need an analyte containing Fe2 plus ions. This is the analyte containing Fe2 plus ions. That is ferrous sulfate solution. That is our analyte. And we need an acidic medium, so we are adding sulfuric acid to the beaker. Then we are dipping a platinum electrode, and a calomel electrode is coupled with the platinum electrode, since we need to measure electrode potential. Since we need to measure the electrode potential, we have to couple a calomel electrode with the platinum electrode. Those points are clear, right? Okay. Then about our titrant, which is taken in the burette. That is ferric ammonium sulfate. Ferric ammonium sulfate solution is the titrant. In ferric ammonium sulfate, cerium exists in the 4 plus oxidation state, Ce4 plus. So our apparatus and the setup is ready. We have to perform our experiment. For that, we are adding 1 ml titrant, 1 ml ferric ammonium sulfate to the beaker. Then there will be a change in the potential or EMF. There will be a change in the EMF. And that value is noted. For 1 ml of 1 ml of Ce4 plus, we got a value for EMF and that value is noted. Again, we are adding 1 ml cerium 4 plus. Again, there will be a value in the voltmeter. That value is noted. Again, we are adding 1 ml cerium 4 plus. There will be a change in the EMF value. That value is noted. So we have values of volume of Ce4 plus and its corresponding EMF. We have volume of Ce4 plus and its corresponding EMF. Based on that value, we are plotting a graph based on the value of volume of cerium 4 plus versus potential versus EMF. We are plotting a graph. And the shape of this graph, it is a sigmoid curve. It is a sigmoid curve. S-shaped curve. Sigmoid curve. You can see here, as we add cerium 4 plus, as the volume of cerium 4 plus increases, there is only small change in the potential. Here, there is only small change in the potential. And it increases, and at this point, corresponding to the volume of Ce4 plus, there is a sharp change in the EMF or the potential. At this point, you can see that as the volume of cerium 4 plus increases, there is a sharp change in the potential at the Calomel electrode. The shape changes. There is a sharp change, sharp increase in the potential. Near endpoint, potential increases sharply. So there is a sharp increase. And from this graph, we have to determine the endpoint of this titration. From this graph, we have to determine the endpoint. You can see here, there is a straight line here. There is a straight line. Half of this value, it will give us the endpoint, the corresponding volume of cerium 4 plus will give you the endpoint. ആ പറഞ്ഞത് ക്ലിയർ ആണോ? പ്രൊസീജിയറും ആ ഗ്രാഫ് പ്ലോട്ട് ചെയ്യുന്നതും ആ ഗ്രാഫിൽ നിന്ന് എങ്ങനെയാണ് എൻഡ് പോയിന്റ് കിട്ടുന്നത്, അത്രയും പോയിന്റ്സ് ക്ലിയർ ആണോ? റിപ്പീറ്റ് ചെയ്യണം ഞാൻ. ഓക്കെ, അത്രയും പോയിന്റ്സ് ക്ലിയർ ആയി. ഇനി അവിടെ നടക്കുന്ന റിയാക്ഷൻസ് എന്തൊക്കെയാണ്, അതെന്തുകൊണ്ടാണ് ഈ ഒരു പോയിന്റ് ആകുമ്പോഴേക്ക് ഒരു ഷാർപ്പ് ഇൻക്രീസ് വരുന്നത്, പൊട്ടൻഷ്യലിൽ ഒരു ഷാർപ്പ് ഇൻക്രീസ് എന്തുകൊണ്ടാണ് വരുന്നത്, അതിന്റെ പിന്നിലുള്ള റിയാക്ഷൻസ് ആണ് നമ്മൾ ഡിസ്കസ് ചെയ്യുന്നത്. During our titration, we are adding cerium 4 plus to the Fe2 plus ions. And we know in the redox titration, there will be a redox reaction between analyte and the titrant. Here, cerium 4 plus gets reduced to Ce3 plus. As the cerium 4 plus reaches to this solution, it gets reduced. Ce4 plus changes to Ce3 plus. And the Fe2 plus ions in the solution gets oxidized. Fe2 plus gets oxidized. Fe2 plus changes to Fe3 plus electron. This is the reduction reaction and it is the oxidation reaction. So together we call it as redox reaction. This is the redox reaction happening during this reaction, this titration. And due to this oxidation reaction, the electrode potential of the indicator electrode, that means against the platinum electrode. The potential of the indicator electrode increases. As we are adding cerium 4 plus and there will be oxidation of Fe 2 plus ions, correspondingly there will be increase in the potential, increase in the EMF value. Near the endpoint, the potential increases sharply. There will be a sharp increase in the potential. What is the reason behind that sharp increase? What is the reason behind that sharp increase? Before endpoint, redox electrode potential is lower due to Fe3 plus bar Fe2 plus system. You know, this is the portion before endpoint. This is the portion before endpoint. Here there is an electrode. Here there is an electrode that is Fe3 plus bar Fe2 plus. This is the electrode before endpoint. Fe3 plus bar Fe2 plus is the electrode before endpoint. And its electrode potential, it is equal to 0.77 volt. Before the endpoint, in this region, the electrode was Fe3 plus bar Fe2 plus, and it has an electrode potential of 0.77 volt. As we are increasing the cerium 4 plus ions, means as we are adding the titrant, there will be oxidation of Fe2 plus, and at the endpoint, there will be no more Fe2 plus. The whole Fe2 plus present in the solution will oxidize to Fe3 plus. At the endpoint, no more Fe2 plus to get oxidized because the Fe2 plus ions present in the solution got oxidized to Fe3 plus. There is no more Fe2 plus ions. So there will be another electrode Ce4 plus or Ce3 plus. At the endpoint, the electrode changes from Fe3 plus to Fe2 plus to Ce4 plus bar Ce3 plus. This will be the electrode at the endpoint. And its electrode potential is 1.60. Before the endpoint, our electrode potential is 0.77 volt, and after the endpoint, the electrode potential is 1.6 volt. That is why there is a sharp increase at the endpoint of the reaction. Clear ആണോ എന്തുകൊണ്ടാണ് അവിടെ ഒരു ഷാർപ്പ് റിയാക്ഷൻ ഷാർപ്പ് ഇൻക്രീസ് വന്നതെന്ന്? എൻഡ് പോയിന്റിന് മുമ്പ് വരെ ആ ഒരു ഇലക്ട്രോഡ് എന്ന് പറയുന്നത് എൻഡ് പോയിന്റിന് മുമ്പ് വരെ ഉണ്ടായിരുന്ന ഇലക്ട്രോഡ് Fe3 പ്ലസ് ബാർ Fe2 പ്ലസ് ആയിരുന്നു. അതിന്റെ ഇലക്ട്രോഡ് പൊട്ടൻഷ്യൽ 0.77 വോൾട്ട് ആയിരുന്നു. എൻഡ് പോയിന്റ് എത്തുമ്പോൾ സൊല്യൂഷനിൽ പ്രസന്റ് ആയിരിക്കുന്ന Fe2 പ്ലസ് അയോൺസ് എല്ലാം Fe3 പ്ലസ് അയോൺസ് ആയി കൺവേർട്ട് ചെയ്തു. ഇനി ആ സൊല്യൂഷനിൽ Fe2 പ്ലസ് അയോൺസ് ഇല്ല. സോ ഒരു പുതിയ ഇലക്ട്രോഡാണ് ഇവിടെ സെറ്റ് ചെയ്യുന്നത്. ഈ ഇലക്ട്രോഡ് മാറി പുതിയൊരു ഇലക്ട്രോഡ് സെറ്റ് ചെയ്യുന്നു, Ce4 പ്ലസ് ബാർ Ce3 പ്ലസ്. ആ ഇലക്ട്രോഡിന്റെ ഇലക്ട്രോഡ് പൊട്ടൻഷ്യൽ 1.60 വോൾട്ട് ആണ്. യു ക്യാൻ സീ ഹിയർ എത്രമാത്രം വാല്യൂസ് ചേഞ്ച് വന്നു. ഈ ഒരു ഇലക്ട്രോഡിന്റെ വാല്യൂവിൽ നിന്ന് ഈ ഇലക്ട്രോഡിന്റെ വാല്യൂവിൽ എത്രത്തോളം ചേഞ്ച് വന്നു. ആ ഒരു ചേഞ്ച് ആണ് ഇവിടെ ഈ ഷാർപ്പ് ഇൻക്രീസിന് കാരണമായിട്ട് പറയുന്നത്. ക്ലിയർ ആണോ?